Yeah, I'd like to first of all thank Ramiro Lafuente, who has been one of the organizers for from the beginning, um, and who is now, because of other commitments, has moved on. And I'm very excited to welcome to the organizing committee for the seminar Catherine Searle and Anna Fino. And it's a pleasure to welcome Marcus Antonio. Oh gosh, I'm sorry. Marcoti, am I pronouncing it right? Um, I'm sorry, I didn't ask you how to pronounce your last name.
Okay, Marrocos, like the country.
Oh, okay. So sorry. Who will be
Oh, don't
speaking
worry.
on the generic irreducibility of the spectrum, the Laplacian on homogeneous spaces, algebraic criteria, structural abstractions, and discrete analogues.
So, so good afternoon, everyone. It's a good pleasure for me to be here today. I'd like to say thank you to Professor Laurev to invite me to be here today. So, today I'm going to talk about generic irreducibility of the spectrum of the Laplace operator in a very specific case, the homogeneous spaces. Let me tell about something about my history with the problem. I've been think of it or in very different ways for my whole career, but I'm just learning the problem. I must never solve it, but today I'm gonna tell you something that my co-working Diego and I have been done in the few years ago. So let me tell you how this presentation will be organized. We start with motivations, some algebraic framework, some explanation about complex and real simplicity, and properly compact symmetric space, positive case and obstructions from the work in Petrecca and Röser, circle bundles when isotope splits, also the contribution from Petrecca Röser, overgroups and commuting operator. This is searching for new examples. This is a work in progress. So if anyone have any tips, I'd love to hear you. And the next, I'm going to talk about generalized Laplacians on bundle, but and hidden symmetries perspective. And I'll finish this talk talking about discrete analog, considering gray Cayley graphs and weighted Laplacians. So let's start. Uh, Let me do this. Okay. Yeah, minute. So the main reference for this talk today is the Dora-Schulz general irreducibility of the Laplacian eigenspace on certain compact Lie groups. The Petrecca Röser irreducibility of the Laplacian eigenspace of some homogeneous spaces. Castle-Kobayashi invariant differential operators on a spherical homogeneous space with overgroups, and the Oliveira and Marrocos hidden symmetries in generalized Laplacians on homogeneous spaces. And the last one, Marrocos Diego et al., generic spectrum of the weighted Laplacian operator on Cayley graphs. Let's get started. So today I'm gonna about the Laplacian and the eigenvalue problem from the Laplacian operator. Here we consider only compact case, so the eigenvalues are discrete and the eigenfunctions is a complete system basis for the L2. And the perspective of the problem here is start with Uhlenbeck, who showed that for a generic metric and a compact manifold, Laplace Beltrami operators the eigenvalues of the Laplacian operator are always simple. That's it. They have multiplicity 1. This is an interesting consequence here, as you see sooner. The generic metric cannot have a isometry group big, otherwise you have a higher multiplicity. So the generic metric has a few, or could have a few isometries inside of the group. Okay. So in the D-manifold case, let M be compact and G a compactly group acting on M. Consider M G the space of the invariant Riemannian metric of the class K positive. You could take a smooth manifold, a smooth metric, but it is not important for today. And the invariant metric G is a real simple, G simple, if every eigenvalue now has its eigenspace as a irreducible real G module. Once the Laplacian commute with the isometries, we cannot expect that the eigenvalues it's simple anymore, because it's eigenspace, it's always a G module, and if the group is big enough, we always have some irreducibility graded dimension of irreducible representation greater than 1. So our principle today is real G simplicity should be generic inside of NG. That's the question that a lot of people try to answer. Let me tell you some contributions, recent at least. This is not the final list. There is a lot of contribution, but this one is recent. We can split the problem in three cases. The finite, the compactly grouped with positive cohomogeneity, and the transitive ones. So the first good answer for this problem, considering G finite, was given by Zeldage. But it's not for every G. There is a relation between the dimensions of irreducible representation of G and the dimension of the manifold. This obstructions is not a natural obstruction. It's the method fails, not the problem. It's not a genuine problem. Okay, in compactly grouped with positive cohomogeneity, we have some contributions as well. José Nazareno, Vieira Gomes, and I, we deal with the case where G manifolds are trivial principal bundles, and Jung and Zeldage working on Kaluza-Klein three-folds, manifolds, and Chattijojo Sutton working on torus invariant matrix. All of these three cases have in common that his argument use as a fundamental tool the infinite dimensional space of parameters. What I mean by that is the space of G invariant matrix, it's big enough to split the eigenvalues. So in these three cases, that's what's gonna happen. If you restrict yourself only in a few parameters, the problem becomes harder. This is exactly what's happened when we consider the transitive actions G on M. In this case, we don't have an infinite dimensional parameter anymore, and usually the usual analytical tools fails to help to understand the problem. So the techniques changed the area, and now we have to use representation-theoretic theory to understand better the problem. So we have a lot of contribution. I didn't put here, but Berger also contribute with this problem, but we have recent contribution as well from Dorothy Schueth, Petrecca Röser, and Oliveira Marrocos. Okay, let's go start with some definitions and notations. Here, K will always be a closed subgroup, and we consider M an homogeneous space. Then the space of infinite functions on M, complex infinite functions, is identified as a functions defined on G and K invariant. We denote G hat of the set of the irreducible complex representation of G up to isomorphism. This is called dual object of G. And for any V in this set, we define the K fixed subspace and a spherical dual. This one is the dual object restricted to VK space. Okay. When we consider the matrix coefficients, we have a natural embedding for the tensor product inside the infinite M functions. Okay. So our first tool here is the Petrecca theorem that said that we can split those L2 space of functions into isotypical spaces whose encode all the copy of the same irreducible representations in the class. So this space L2 can be broken in a direct sum of the space IV star, and this space are finite dimensional, but we have an infinite quantity of them. Okay, so again, here we consider a G representation always spherical, who says the dimensions of the key is greater than 0, and we set again we already defined it. The subgroup K is spherical if every spherical representation V satisfies this property, the dimension Vk is equal to 1. It's a huge simplification to the problem, by the way. When we have a positive or greater than 1 dimension for this space, the problem to splitting eigenvalues become harder, by the way. At least for me. So in this case, the pair is called a symmetric pair, and the homogeneous space is called a spherical homogeneous space. Today, we are going to talk about only about spherical homogeneous space. As you can see, the easy case, in this case, it still is very difficult. Okay, let V be an irreducible complex G representation and the set of endomorphism G invariant. We can classify the representations in 3 types: real type, quaternionic type, and complex type. When we have an equivariant endomorphism J with these 2 properties. It's a structural map. We can also characterize the representation by compare it from the dual one, and if when we have the representation V and its dual equivalent, so we have real type or quaternionic type. When this kind of it doesn't happen, we have a complex type representation. Okay, so more definitions and properties. Here we consider G invariant matrices on M. And the set can be characterized as a k-invariant in a product on a complement M of the splitting in the G algebra. We also can consider an inner product on G, inducing a Riemannian matrix in an orthonormal basis of the Lie algebra G. Then, on the left invariant matrix, we can express the Laplacians in this way. So here we start to take, advantages of the whole realm of symmetries. So when we restrict ourselves to a specific irreducible representation, the Laplacian has a new form, and it can write down exactly like this. So this form helps us to understand better what's happened when we have a joint eigenvalue. Let me explain what I mean. So we can express the right part of the Laplacian as a sum of the quadratic of the Lie basis y e square. And when we look at the Laplacian like this way, we see that the only contributions that come from the metric, it's contained in this operator here, Laplacian vk. So we're going to study this guy here. Just a comment. When we are in a spherical homogeneous space, vk is one-dimensional. So we have the more simple expression for this operator, Laplacian vk. And even in this situation, the problem is still not easy. Okay, again, we can characterize the high multiplicity of the eigenspaces just taking the specific eigenspaces and looking how it's split in irreducible representation of G. So what we would like to get is a metric where each one of these eigenspace would be a irreducible representations of G. So the multiplicity can be expressed in terms of the Laplacian vk in this way. The vk restricted on a specific, the Laplacian restriction on a vk has only simple eigenvalues, but we are in a spherical homogeneous space, so we always have the first condition satisfied immediately. And the second one, when we take two different Laplacians associated to different irreducible representations, they cannot share eigenvalues. We call these the spectral collisions when they have the same eigenvalues, when they share at least one eigenvalues. Okay. So from now on, let me explain what I mean by complexity simplicity. When we look at the eigenfunctions as a complex functions, we look in the space as complex representations of the space. So we say that the metric G is complex G simple if every eigenspace is irreducible as a complex G representation. It's not happening always, but we have a criterion to verify when we can have this kind of G simplicity. So Petrecca Röser just describe it in details. When is it possible? Okay. Now, for understand how we can split the eigenvalues, we must understand a little bit more about the space of parameter. So here we have the space of the invariant matrix can be identified that could be identified with the space of the 0 to symmetric positive definite. And with I'd like to point out this space here is a finite dimensional space again. And the map would associate a matrix to the Laplacian of Vk is linear in the integers of B. This is a nice thing, but it's not help at all. So, a little bit more structures about this representation space. When we consider the isotropy representations of K in the tangent space, we can split the space in a sum of irreducible in equivalent K modules. They can have multiplicity, but in this case here, when we consider only irreducible K modules, the space of parameters become simpler. And again, for us, it's the bad news because we have less freedom to perturb the operator, to change the eigenvalues. So the expression for the Laplacians restricted to Vk is also extremely simple. As you can see here, Ci is just the Casimir operator from each factor mi. Okay. So if you want to understand what's going on with the splitting eigenvalue, we are in a finite dimensional case, and we can look at the characteristic polynomial and try to understand if the polynomial has eigenvalues with multiplicity or not. So we have here a very algebraic criterion to decide when these Laplacians could share an eigenvalue or not. So the problem sounds simple because only we have to do is look some polynomials and test if they identical 0 or not. But fortunately, it's not easy to do as well in the practical way. Okay, so we have a very natural criterion, algebraic criterion for existence of the metric, is it simple or not. All that you need to do is to verify these three cases here. And if you find one metric with this property, we also have a residual set of metrics who satisfy this possibility. This characteristic is just simple to be simple. Okay, let me tell you some perspective about this comment. Even in cohomogeneous positive, this is also true. If you find one metric with this property, we can find a residual set of them. But follow from the analytical arguments. So let's consider the first case, the G-simple spectrum of symmetrically reducible space. So the first result about this problem came from Berger, Goduchon, and Mazet, who tells us that if the identity component of K acts transitively on the unit sphere under the isotropy representation, then we have a G-simple spectrum. So we can verify these simples. Now it's simple. We can verify this for a lot of examples. But Petrecca Röser give us a more details about the existence of this kind of metric or not. And they prove that an irreducible symmetric space GK has this simple metric if only if the rank is equal to 1. Now, I'd like to share the argument, why this is true, and how this idea gives us some another ideas to deal with new examples. Okay, let's start with the proposition. Again, Petrecca Röser. Let's deal with rank greater than 3, greater or equal 3. In this case, you give me a minute. Okay, now I see. So let me explain in general how the argument works. In this spherical type, we can consider the dominant restricted weight and write down like this. For this dominant restricted weight, we have a fundamental formula who tells us who is the eigenvalue of the Laplacian associated to this dominant. So this formula is a polynomial and tells us who is the eigenvalue. So if you want to understand what's going on with the Laplacian, all we have to do is to understand these polynomials. But let's see what it tells us. Okay, if you want to prove the results, the metric is not just simple. So all you have to do is to show that we have two dominant that have the same eigenvalues. The perspective here is pretty clear. We have a polynomial, it's not injective in the dominant. The analysis becomes injectivity of polynomials. So we can return the rank 1 case. This polynomial here, it's a quadratic polynomial once the Laplacian is the second order operator. So when we have the case with rank 1, this polynomial is a quadratic polynomial in only one variable. So now it's simpler to understand why we can have these functions injective. But for rank 3 and more, it's not obvious anymore. Okay, let's see the argument. So we start choosing simple restricted roots and fundamental restricted weights and fix a picked two simple restricted roots, beta 1 and beta 2, with the same length, such that we produce an element orthogonal to the delta. And this argument works only in 3 or greater rank. It's a dimensionality argument. So Petrecca Röser built a reflection with a very simple formula, as you can see. So this reflection fixed the delta and also fixed the polynomial, the fundamental polynomial. So if we able to show that the x is the dominant such that R alpha of this dominant is another dominant, so we construct a map between dominants who produce the same eigenvalues. This is the spirit. Again, this reflection do not come from the group action. These reflections come from the inner structure, the weight structure. That's why it's interesting. Even the existence of this kind of reflections is interesting, at least for me. And I'd like to explore this more later. Okay, so that we need to verify is we can produce another dominant such that R alpha who is also a dominant. Now, oh, sorry. Now the dimension is crucial again. So you can produce exactly like this. It's a arithmetical argument. We must choose these parameters large enough to guarantee that the reflections has all these coordinates positive. It's enough to build this image as a dominant. So here we have a point. We have a point. We don't have isometries enough to split the eigenvalues, but we have another structure applications that make the same kind of transformations with the eigenvalues. I'd like to suggest that this kind of reflection is a hidden symmetry, or at least another kind of symmetry. Okay, so in rank 2, we cannot reply these arguments. So we take the classifications of the all irreducible symmetric compact symmetric space and do it one by one. Do it what? We look at the polynomial, it shows that it never injective again. So we can produce by hand the parameters that share the same value in the third term polynomial. Okay. So from the table, we can take the polynomial, do a lot of computations, and finally find some occasionally degeneracy. Um, I'm not able to do what I'm going to say so far, but at least I'm thinking about it. I don't think this is an accidental degeneracy. It must have a clear structural explanation, but I don't get this explanation so far. So the not injective imply eigenvalue collision, so not just simple metric. And we finish the proof. But let's see what the proof tells us. The setup here is irreducible symmetric space of rank L. The isotope representation is real irreducible. Then the invariant metric is unique up to scale. Hence, G non-simplicity is detected by the normal metric. Okay, it's the result before that we presented before. So we have this polynomial here, and what is said to us? G simplicity forces an injective principle. Distinct spherical labels should not yield the same eigenvalue. Hidden symmetry imply collisions, as we see from the reflections, Petrecca Röser reflections. Okay, so let's try another example, also from Petrecca Röser. This shows us that homogeneous circle bundles also have geometric, the simple metric, but they use an interesting subjacent structure. They use the double, not double, the chain of vibrations, like this one. These structures was essential to prove the result, but they use it as well a classifications of the space which have this vibration, this special vibration. Okay, let's go into the argument. Why this vibration is important? Again, when you're going to split the tangent space, we can use this structure, this subjacent structure, and understand how to split the space of the G-invariant metric. And in this case, did not irreducible isotropy because the isotropy split, but the space of metric now have some freedom. And this is essential to the argument. It is not too much freedom, but it's enough to prove the result. So what they say, what they do? They consider the Casimir operator, the total Casimir operator from the normal metric on G, and write down the Casimir that came from the metric exactly like this, where 802 it's the element that comes from the vibration. This is the new element. So now we have a function that we have to test again if it's injective or not. But now the map has two components, two coordinates. And this was essential for the argument. This is the principle here. We must understand injective map or not, or when it's injective or not. So they prove that a generic SU n plus 1 invariant Riemann metric on total space in total space of the Hopf vibration is SU n plus 1 simple. But the idea is clear here. We need to have more parameters. Otherwise, we are subject to internal hidden symmetries that avoided to the eigenvalues split. Okay. Now let me spend some minutes telling you what we're trying to do now. It's almost finished. It's a simple example, but we consider overgroups in the philosophy of Kobayashi Castle. They also consider a double vibration. Oh, no, not exactly double vibration, but a chain of vibration that help us to understand not the Laplacian, but the algebra of G-invariant differential operator, the whole algebra of the G-invariant differential operators. When the homogeneous space has this kind of structure, we can understand this differential algebra, this algebra of differential operators clearly, and that's help us to looking for information the Laplacian as well. Let me tell you how. So again, the result of the Kobayashi says that the dGTX, the set of the G-invariant differential operators on X, could be generated for the three very natural differential G-invariant operators on the vibration. So our Laplacian lives in the base space, and we can use the overgroup and the fiber to help us to understand what's going on with the Laplacian. How we can do that? So here we have the structure of the GX. This This is a result from Castle-Kobayashi. So every differential G invariant operator can be written like this. The subalgebras commute to each other, left action versus right actions, and we can use this subalgebra to write down specifically our Laplacian in the same spirit that Petrecca Röser did. So we take a very specific example from the list, from the Castle-Kobayashi list, this one. Why I choose this one? And there's nothing special, but I like the space. I like the G2 space. So for me, it was more interesting to try this one. But I I want to understand under the perspective of Castle-Kobayashi splitting algebra, how can use this to understand the Laplacian. Okay, we have the vibration that we need that come from the Castle-Kobayashi result. Okay, so what is the idea? So we took a basis and not basis, but second order differential operators in each one of this algebra, and write down the formula self-adjunct differential operator with order up to 2 using these elements like this. So it's easy to consider the case where C is 0 because the constants are always eigenfunctions associated to the 0 eigenvalues. Okay, our Laplacian can be split in like this. And each irreducible representation has a good behavior as well in these elements of basis. So we can apply the Ferdinand formula here and understand the eigenvalues of the Laplacian as a linear combinations from these elements, from the vibration that come from Castle-Kobayashi decomposition. Okay, so now we have almost everything that you need. Again, we're going to look at the tangent space and split the tangent space to understand if our decompositions is compatible with isotropy decomposition of the tangent space. But this is true, so our Laplacian can change if you take different metrics, but the elements of the basis are the same. Okay, so that you have to do is to show that this polynomial lambda t is injective or not. It's all that we have to verify. And so far, everything is good. I'm not finished yet, but this is a lightning example. What we need to do is a simple argument. If you can say that this function is not sorry, better. If the lambda function is injective, it's easy to argument that we can find parameters whose that the all eigenvalues has only one in represent. I'm sorry, let me try again. If you can show that the lambda function is injective, so we can choose a parameter t such that the Laplacian has not multiple eigenvalues in our sense. Multiples, irreducible representations inside of the same eigenspace. So that's the argument. We almost finished. So this is not a theorem yet. Uh, uh, I would like to say that it's an almost theorem, but the strategy it's completely set, and we almost finished this case. So this is uh, my idea for this problem. We Diego and I just took the mixing from ideas and look at the problem in details and get some new perspective. I don't know, but this is a work in progress. So I have a little bit more time. Emilio, I have more time or not? Maybe not.
Yeah, you have like another 5 minutes. Yeah,
Okay,
or a
okay.
few
Five
more if you need.
minutes. Okay, 5 minutes. It's sufficient. Okay. So let's talk about a little bit hidden symmetries. So as we said before, we sought a structured map that tells us what kind of irreducible representation do we have. So Diego and I using this structure map to build a specific action of the key 8 action, Q8 action, and show that when we have a complex type irreducible representation, we always have this non-trivial action, so we cannot expect complex simple metric, but if you look as a key QH times G, now we have a genericity property once the eigenspaces become irreducible by the actions of this group. This is we would like to call hidden symmetries, or at least one kind of them. Okay, from the Jose Petrecca's argument, we also consider the different hidden symmetry structure that come from the weight restricted root system and weight lattices. Tells us that we can have a lot of dominant with the same eigenvalue. So we consider the map who's doing the permutations between this dominant. So this action could see as a structure that glued together an eigenvalue and make the eigenspace to have a bigger dimension. That's the spirit here. And we know at least one example when we consider the rank 3. So this is kind of a hidden symmetries that we'd like to consider as well. So when we consider the all kind of permutation that we could have in the lattice, we can build on ambiguous actions on the eigenspaces. So this produces eigenvalues that it's not explained by the isometry group. That's the approach here. Okay. Finally, we just considered homogeneous vector bundles and building the whole structure involved, and consider the G invariants, differential operators, in this kind of homogeneous bundles, vector bundles, and look at what kind of hidden symmetries we could have as well. So again, we look at the polynomial and we see that the fiber now helps us to understand the multiple dimensions that we could have in the eigenspace. This kind of hidden symmetries is even bigger. It's a lot of case when to sum up even the scalar case on the fiber bundle case, we always can expect collisions if you don't have too many parameters. That's the point. Okay, so we can build in a biggest action group and tell exactly what's going on inside of each eigenspaces and tell us why is not G invariant or G simple, but is another biggest group invariant and irreducible as well. Okay, this is the precise result. Finish the lecture. I'd like, oh, oops. I'd like to present some results on Cayley graphs. We build a Cayley graphs here using a finite group and choosing a symmetric generate set. This choice is important here. After we choose this pair, we can consider G invariant weights in the space of these weights and build a Laplacian. If we take G invariant weights, the weight and Laplacian is invariant as well. So it's in the same spirit that we had before in the continuous case. Now we consider a weight as a metric in the Cayley graph and a weighted Laplacian as a Laplacian, and we can analyze the simplicity again. It's exactly the same way. But here we have examples with is the simple and it's not the simple. Here we have the table when Cn is cyclic, when we have the Cartesian product Klein, dihedral, alternate, S4. Here we have an interesting example. If you change the generating set, we can lose the properties. We have a generating set when we have the simple, and when we don't. Interesting fact here is the proof relies to analyze patiently polynomials and roots of polynomials. Maybe we can use machine learning to help us to verify these results for biggest group, but so far we made everything by hand, so only few groups we can explore. So this was my ideas for today. This is the references that I use. And thank you for your attention. Questions and comments are welcome. And to finish, oh, I don't believe that. My picture, it's gone. Nobody can see my picture. Oh, I'm sad. Okay. Let's finish with this one.
Oops. Thank you very much for a really interesting talk. Are there questions?
Marcos, when you mentioned the other group, the G tilde group, could you please show the slide? You were talking
What?
about the vibrations, the upper group, the G tilde.
Okay.
When you mentioned Kobayashi.
Okay. Here.
Yes, the group in the previous slide, the group G tilde. Is it supposed to be smaller
No, it's
or
bigger.
larger than G?
It's larger. Sorry.
It's
It's larger.
larger.
Yes. It's an overgroup, in fact.
Okay. And have you investigated the different realization of the sphere? The sphere have several realization with G over K, and maybe may
I
give.
do, I don't get into too deep inside this work, but I have a table, and I took some examples to try my ideas. But I'm working on it to understand this vibration better. But this is not free enough. We have a list with few examples when this kind of vibration happens.
Okay.
Are there other questions? So, did I understand? I don't know if I understood correct. If you don't have hidden symmetries, do you know that you actually have the irreducibility?
Yes.
Yeah. Okay.
Yes.
Okay. So it really comes down. Okay. Are there any other questions? Well, thank you very much. It was a really interesting talk.
We still can.